Good evening, everyone. Happy to be delivering a session in today's webinar. I'll walk through the what I'm going to share today. I'm going to share a session on real-time operating system, which will cover through what is the real-time operating system, the difference between general-purpose operating system and real-time operating system. Let's run through the basics and features of a real-time operating system, simply referred as RTOS further, and the interrupts in real-time operating system, and the difference between a preemptive kernel and a non-preemptive kernel, and tasking. In tasking, we'll talk about multitasking and inter-task communications, and then we'll also talk about context switching in real-time operating system and the memory management in RTOS. I'll also touch about the career scope in real-time operating system field and the essential skill required for you to get into this particular career. Okay. So before we really get into this real-time operating system, let's touch upon the basics of operating system, which is usually referred as an intermediary between a computer and a computer hardware. The significance of this operating system is that it's a software that manages the computer hardware. The hardware must provide appropriate mechanisms to ensure the correct operation of the computer system, to prevent the user programs from interfering and the proper operation of the systems. Okay. There are various definitions available. In simple, it is the kernel is referred as the heart of the operating system, which takes care of managing all the process in turn, which is referred as task that is running in the system. And these tasks has to run in hardware, and this kernel manages what are the various tasks that is going to run right now, schedule various tasks, and manage how these tasks are going to run inside the system. Okay. And again, this operating system is further layered into different architectures, and based on this, we'll see one by one layers of this particular operating system. Before even we get into this, the three important significant functions of the operating system is that convenience. So the operating system should provide a convenient platform for the user experience, and efficiency in performing the given task in an efficient manner. And of course, it should evolve over a period of time to introduce new functions, which is provided by the updates provided by the operating system. Okay. So now let's get into the layers of this particular operating system. Right from the bottom, which is called as the computer hardware, and the next layer is the operating system. Usually the kernel resides in this particular layer. Next, the utilities, and the next is the application program. Usually the lower layer is going to be the hardware, and the top layer is going to be a software that is going to run on this thing. Okay. And this computer hardware, it is the physical component of that particular hardware, like our processor, RAM, memory, hard disk. All these are going to are the components of this particular hardware. And to operate this hardware, we need some control unit to function, and that is what is managed by the kernel, which is part of the operating system. So this kernel takes care of running which task has to execute at which period of time. All these are managed by this particular operating system's kernel. Just like Linux has a kernel, Windows has a kernel, and even Android has a kernel. Go into mobile, get into your settings, you will find which kernel is going to run. Usually our iOS and Android is going to using the Linux kernel, but heavily customized for their particular implementations. And then next to the kernel, we have our utilities running over there. The board support packages, the device drivers are all going to take care of running in this utilities. And it is significant that because we are going to interface, if you are bringing in a new device, let's say USB, when you plug in your USB into your laptop, you would see that the device USB driver is running, and then USB is ready to run right now. You're trying to bring in a new device into the system. So which means that your kernel should know there is a new device, what is the address to access this particular device, what is the memory that I have to allocate to this device, and then how to handle whenever a system call is executed to handle this particular device. All this has to get a handshake kind of a program runs between the kernel and the external. So this device is managed by what is applications called as device driver. Okay. And then finally, we have our application programs running, just like our Microsoft Word, MATLAB, any programs that the user is going to run. So it is the end user who is going to make use of that. Till now, till the utilities, operating system, and the computer hardware, we usually get it from the vendor, but the end user is going to be bothered about only running his application program on top of all these particular layers. So he needs to be provided with an efficient place where he can execute all these operations. Okay. And then, so with this particular knowledge, let's get into the real-time operating system. I can refine this particular real-time operating system as a variant of an operating system that operates in a constrained environment. Please underline the word constrained, because our laptops, let's say any laptops or CPU or your desktop machines or even servers is going to have a dedicated general purpose operating system. So we don't have to worry about how long is this system going to run all these things, because it is provided with enough memory, enough RAM, enough cache memory. Everything is rich over here. But whereas if I need to run in a microcontroller, which is going to have maximum, let's say 1 MB of memory or 2 MB of memory, and then it has to run all the interfacing experiments that it is designed for, there I need to run an operating system for a dedicated task. Remember the word dedicated task. So I need to prepare an operating system which can run in this 1 MB or 2 MB memory devices. Okay, and this is where I need a constrained environment. Again, there is one another function. Sometimes these devices are going to operate in battery operation. So which means that I may not have enough power to run for a long period of time. So if I cannot go and install a Windows operating system on these devices, or a Linux for the matter. So we need to look in for other alternatives which can run in a constrained environment. That is where this customized operating system called as real-time operating system comes into the picture, where I handle the computer memory and processing power, which is very limited in nature, and I'm going to operate these devices. And these provides their services for a definite period of time. Okay, the word definite period of time implicates to the next point, which is called as hard, soft, and firm RTOS, which is referred as soft real-time system, hard real-time system, firm real-time operating systems. Okay, so first of all, the soft real-time system, which means that these are usually which will meet the time constrained deadlines. So there is a process called what is called as preemption. Okay, it can preempt the process that is running, and it is usually within a few milliseconds. And then if I have a hard real-time system, it is a definite deterministic systems. Okay, which means that if something has to happen at this instant of time, and it should happen at that instant of time. Let me differentiate between these two things, soft and hard real-time systems. Usually, the operating system that is running in our mobile, long time back, it was referred as embedded operating system. Now we have referred it as general purpose operating system. Let's say that older Nokia 1100 mobiles we were working with, which is running in a Symbian operating system. Okay, and then there I'm, let's say that I'm using a Facebook application, and I'm hearing a songs, and then there is a call that is going to come. All these are defined as 3 different tasks. Facebook application running is one of the tasks. Second one, hearing a song on a music player is a second task. And then third task is a call that is going to come through a dialer. Okay. So what would happen right now is that I'm browsing through the Facebook application. Parallelly, I am also listening to the music. Okay. So these 2 tasks are time being that is running in the system. And let's say if a call is coming right now, okay, and due to some internal concerns in the hardware, if the call receiving feature takes 1 or 2 seconds delay, I'm fine with it. Okay, 1 or 2 second delay in receiving the call will not affect my performance of this particular system. It's fine. I shall go through it. Okay, but let's say I'll put the same kind of an application in a different perspective. In a, excuse me, I'll put the same application in a different perspective. Let's say that I'm driving a car right now, and then my car has met with an accident right now. Okay, so which means that this moment, if there is a catastrophic event, which is the accident is referred as catastrophic event. So when I met with this accident, what should happen is instantaneously the airbag should pop up, right? And that airbag should pop up in 0.2 seconds. That is the maximum duration or the protocol in the automotive industry. So this airbag should pop in 0.2 seconds. If it's not popping in 0.2 seconds, usually the measured time between our body hitting the vehicle is that usually 0.5 seconds to 1 second response time, depending on the impact of that event that has happened right now. So if an event has to happen in 0.2 second in this particular scenario, it has to happen at that 0.2 second. There is no delay accepted. There is no lag that can be accepted in these particular scenarios. Those systems are called as hard real-time systems. Okay, where a lag of even 0.1 seconds cannot be accepted is a critical event. Okay, so we have to prepare our real-time operating systems, hard real-time operating systems. So in embedded operating systems, kind of Symbian I was mentioning, soft real-time systems is okay for me. And then finally, the firm real-time operating system, it is having a certain time constraints which are not strict, but and may also cause undesired, but yet these effects are acceptable. Okay, if I have a firm real-time operating system which sits between this hard and soft real-time system, have some time constraints, and if it does not happen, I am okay with this particular event, but still it has to manage. Okay, how the structure of real-time operating system differs from the layered view of operating system is that we have our custom hardware. Okay, there we would have a generic hardware. I may have a Intel i5 or Intel i7 processor, and then I'll have my kernel sitting on top of it, and then I'll have my device drivers, and then finally I'll have my applications running on it. Here we have a custom hardware. Usually the real-time operating systems are always built knowing what is going to be the hardware, whereas general purpose operating systems are not built that way. It is the word itself means I don't have to worry about the hardware. We know that these are the hardware that I can work with. But whereas in real-time operating system, I should know only on this particular hardware my software is going to run. Okay, so for that is why I referred it as custom hardware, right? The next is my the kernel. Okay, the kernel, of course, the kernel comes packaged with a board support package called as BSP. What we referred as device drivers in the general purpose operating system, we customize and refer to this board support packages. You can understand from the name because I'm using a custom hardware, which means for that particular hardware, my kernel should issue the task and it should know to which hardware it is going to talk. So it should understand to which hardware it is going to talking means then it should know the device driver respective to that particular hardware. That is what we refer it as what is known as board support package. If I'm going to use an ST microelectronics, I need to bring in only the board support packages for ST microelectronics. If I'm going to work with an NXP processor, then I have to port only the NXP's board support package. So like that, you should identify which microcontroller you are going to work with, and that board support packages are put into this RTOS kernel, and then this RTOS kernel is going to run. And this application is a dedicated task that is defined in this particular RTOS. I may have n number of tasks that is going to run in the system, and we manage all these tasks through a memory management unit, and then handle this task and then execute these tasks on this particular hardware. Okay, so Next, what are the characteristics of this particular real-time operating system? As I already mentioned, it is going to operate on a constrained memory. So it is going to have very little memory. It is going to operate on minimal power consuming, minimal power available device, sometimes on a batteries, let's say. And then second is that it's working on a resource constrained device. Again, this comes as in addition to the first point. I will have only 2 MB memory available, sometimes even KBs of memory, 16 KB, 32 KB memory, but still my real-time operating system has to run over there. And it should be, it is going to run on a predictable response time, which means that, let's say that if I'm operating as many tasks in my Windows operating system, I don't have to worry about how long this task is going to run. When the job is completed, it will give up the processor, and then next event takes up running the processor time in the system. Okay, because of the highly efficient processor, we see as if only one task running in the system, whereas there will be multiple tasks that is running in the system. Okay. But whereas the case in real-time operating system is that each of the event is going to be deterministic in nature. It is always known this is going to run only this amount period of time. Okay, so that is significant in a real-time operating system, and based on which scheduling algorithms are prepared. And then operating in an unpredictable environment. Sometimes we don't know what event may happen. So we should be prepared for a catastrophic event. So we should understand what may happen out of it. And then we should program for that particular event, for a deterministic event to happen at that particular instance, for an unpredictable event. And then priority-based task switching, sometimes referred as context switching, also is going to happen. And some other points that I can add here is that these real-time operating systems are going to be preemptible in nature. I did mention it as preemptive scheduling. Okay, it's a CPU scheduling technique that actually works by dividing the time slots of a CPU to a given process. Okay, there are various CPU scheduling techniques, right from round robin, priority based, shortest remaining time first algorithm, EDF, all those things. Okay, and then there are non-preemptive scheduling. These non-preemptive scheduling also is part of your general purpose operating system. Okay, so moving on from this place to interrupts. So this interrupts are an undetermined event that is going to happen instantaneously, and these interrupts are usually handled by what is called as interrupt vector table, IVT. Okay, and there is an interrupt handler which actually manages all the interrupt that is getting generated. The interrupts may be software or hardware in nature. Okay, and it is an event that is requested because that event has to happen at that instant of time. In general purpose operating system, interrupts can be managed because only after the current task that is running in the system gives up a task execution, the next task will take up that particular event. So interrupt will manage it. But whereas in real-time operating system, interrupt is significant. If a priority task is requesting the processor time, the lower priority task has to give up the processor time, and interrupt takes care of servicing that particular events during this particular scenario. And most RTOS kernel issues task using this interrupt vector table. Okay, so let's say that once our bootloader boots up, there is a defined interrupt vector table defined in my memory segment, and there is my application code running. Okay, and if there is an interrupt that is being generated, this application code has to provide the interrupt vector table for its period of time to complete the task that it is requesting, and then give up the interrupt vector. Interrupting vector will finish the task and then request the next event to run this particular task. Okay, next in this scenario is the multitasking and the inter-task communication that is running inside the system. Okay, you can see a small illustration here. I have 3 tasks scheduled inside my CPU, and virtually see that all the tasks are parallelly running in the system at different time intervals, right from T1 to Tn, which is progressive in nature. But actually, what is happening inside the CPU scheduler is that only one task can run at any given point of a time. Okay, whether it is a low frequency or a high frequency system, that's a different immaterial to it. Only one task can run at any given point of a time. So what would happen is that task 1, T1, will run for a certain amount of time and it will give up the processor. And then task 2 takes up its own time to complete its period. And then task 3 will take up some amount of time to complete its period. Again, task 1. So it will be scheduled. It's similar to what is called as round robin scheduling algorithm. Task 1, task 2, task 3. Again, task 1, task 2, task 3. Okay, but it depends on the scheduling algorithm. Different scheduling algorithm will have different things. And again, the T1 value, T2 value, T3 value may not be equal. It may be difference in nature. Task 1 for T1 will take some amount of time, and it may not be the same amount of time for the task 2 to execute. It will be some other period of time depending on the task that it is needed to execute. But what happens is that this task 1 is divided into batches and it takes some amount of time to execute each of that particular critical event.